This tutorial is going to go through how to run a basic thermal conductivity calculation using the PuMA GUI. So the first thing you're going to do is open up a terminal, type in conda activate PuMA, and then PuMA GUI.sh. At this point, the PuMA GUI should appear. Obviously, in order to run a thermal conductivity simulation, you have to have some material to calculate the thermal conductivity on. For the purposes of this, we'll just generate a simple spherical structure. Let's generate a sphere structure with, say, 128 by 128 by 128, average radius of 10. We'll allow the spheres to intersect, and we will put a porosity of 0.8. All this is explained in more detail in a dedicated tutorial for random sphere generation if you're interested. So generate. Just to see what we're working with here, let's do a 3D rendering. As I've gone over in other tutorials, if you generate a material in PuMA, it defaults to the grayscale range of between 0 and 127 as void, and 128 to 255 as solid. Now, the reason that we have it be a continuous range, you might think, well, why isn't it just 0 and 1? And it's because for visualization, for exporting STLs, as well as for some of the solvers, including the random walk tortuosity solver, having the extra precision in the triangulation that you get from a more continuous grayscale range is actually quite significant. Same thing with calculating surface area, for example. It matters quite a bit. So for this reason, we default to this 0 to 127 void, 128 to 255 solid. So let's go ahead and generate the 3D rendering of that. Okay, here we go. You can see what we're going to be calculating our thermal conductivity on. So to calculate the thermal conductivity, click on Material Properties, Thermal Conductivity. By the way, thermal conductivity and electrical conductivity are going to be essentially the exact same in terms of mechanically how to run them. So I'm just going to show you how to do the thermal conductivity, but electrical conductivity is going to be exactly the same. So for the thermal conductivity, the first thing you have to choose is the method that you want to run. You have two choices. You can either run the explicit jump method or a finite volume method. If you run a finite volume method here, you have a little bit more flexibility in terms of boundary conditions. You can run in the side directions, either periodic or symmetric. In the simulation direction, it's going to be Dirichlet. Or if you run the explicit jump method, which is what we'll run in this case, then you are going to run periodic in all three directions. That may be appropriate depending on your material. It may not be. In the case of our material, since it was artificially generated, the structure itself is in fact periodic, so it is appropriate to use periodic boundary conditions. Next, you're going to select the materials that you want active. So we have 6 here. If you need more than that, then you can reference directly the PuMA API, or you can use the PuMA C++ API, or you can use the Python API, and you can have as many material phases as you want. But if you're going to do in the GUI, it needs to be somewhere between 1 and 6. So for each material phase, you have to specify the grayscale range. So in our case, for the void phase, 0 to 127. And then you specify the thermal conductivity of that void, of that phase. In case of air, standard temperature pressure, in SI units, we're using 0.0257. Next is the second phase, which is going to be 128. Since these are inclusive, it should not be 127, 127. It should be 127, 128 to 255. And we're going to specify a value of, say, 10, which is kind of arbitrary because this isn't a real material to begin with. So let's go ahead and launch that. I'm going to say begin calculation. It should run extremely quickly. While it's running, I want to point out these options down here. We have solve in directions X, Y, Z. So if you want to solve in each of the 3 directions, they should each be checked. Iterations is how many iterations the iterative solver will run before giving up. 10,000 is usually default. Same thing. Accuracy is when the iterative solver will will say that we're close enough to steady state. Number of threads, since we're just running this on my MacBook, it has 4 processors, so that could be up to 4. If you set this to be 0, it will just default to whatever the maximum number of threads on your system is, which in this case, of course, is 4. Now you can see the simulation finished running, and the output is here on the right. So we can see we have a thermal conductivity of 0.06 in each of the principal directions here in the X, Y, and Z directions. And since the material is isotropic, we should expect these to be about the same in each direction, which it in fact is. So just for fun, let's go ahead and actually visualize this field. So I'm going to say let's output the temperature field here. So once this is run, let's output the temperature field, and we'll output it to VTK. Let's just do it to the desktop. So test temperature. And it saved the, you can see it here in the desktop, it saved in X, Y, and Z directions for each of the 3 simulations. So let's go ahead and also output, let's output the 3D TIFF also to desktop. Test sphere TIFF. Here we go. And then let's output the STL. So export the STL, and we're going to export 128 to 255. Let's also export that to the desktop. Okay, so now let's visualize this field in ParaView, which is kind of my go-to visualization software. Of course, you could use whatever software you like. I'm going to use the TIFF to generate just the outline here. Let's use the STL. And I forgot here, it has a weird spacing, so I need to change this to 1, 1, 1. Apply. Here we go. And then we are going to also visualize the temperature field. Okay, now the temperature field, let's go ahead and crop it. So let's visualize it as a volume. And let's crop it. So here we go. Let's create a slice in the, let's create it in the Z direction. Go apply. And here you go. You can see our material, and you can see what the temperature field looks like. So specifically in the X direction, we had a temperature of 0 on this end, temperature of 1 on this end, and then we converged it to steady state before calculating the overall flux through. And from the heat flux through, we then backed out what our thermal conductivity is. And that's how we got to this thermal conductivity value of 0.6. So that's pretty much it for just a basic introduction of running a thermal conductivity simulation. If you have any questions, please reach out to me at joseph.ferguson@stanford.edu or reach out to federico.semeraro@nasa.gov. If you send out to an email out to either of us or both of us, we'll get back to you as soon as possible to answer any questions or deal with any issues that you may be having.